Thank you, Mark, and thanks to all the organizers for giving me the opportunity to report here on this joint work with my student, Matthias, who's also in the audience. And this is concerned with something rather simple, confidence sets for means, except that here the data are on a circle. So let me try to explain this. So I'm looking at circular data, so I assume I have IID data, x1 to xn, that take value on this unit circle, and I'll occasionally identify the circle here with an interval minus pi to pi as usual. And this occurs in practice rather often. You might consider wind directions, say, or other periodic data, say the time of admittance to a hospital unit, and you want to do statistics with such kind of data. And the simplest statistic you could think of is the mean, admittedly, I would say. And so we'd rather like to have confidence sets for means here. Now, there is some slight difficulty here. The circle is not a vector space, so averaging won't work in some sense, but luckily, already Fréchet had an idea what one could do in such a situation. Since if you have a metric space, then you know in the Euclidean space, the mean is the minimizer of the sum of squared distances. And similarly, of course, if you have a distance, you can define what is nowadays called the Fréchet mean, which is a minimizer of expected squared distance to your random variable. Or if you have data, you can define the empirical analog. You minimize the average square distances to your data points. And so the function that you're minimizing, I denote here by f, and in the population version, an fn hat to denote the so-called Fréchet functional. So I'm looking for minimizers of this functional. Now, luckily, the circle is a compact space, and the distance squared is a continuous function, so we will have existence of the minimizers, but unfortunately, it may not be necessarily the case that these means are unique, right? At least if we work with the intrinsic distance on the circle, which is arc length, right? So the distance I'm choosing on the circle is arc length here. All right. So now that we have defined our means as minimizers of some Fréchet functional, how do we construct confidence sets for such means? That's my question. And of course, you could say, well, the classical approach would maybe be to use asymptotics, right? If we have a central limit theorem, then you could construct an asymptotic confidence set from this central limit theorem. And in fact, it's, one can prove, and McKilliam and others have done this, and also Stefan Huckermann and me in a slightly more general version, that if your data is such that, first of all, your mean is unique, otherwise the central limit theorem won't make much sense, right? And if you have another property, namely that the density at the point opposite your mean is not too large, it's smaller than the uniform density, then you get a kind of central limit theorem for this mean. However, if the density reaches the uniform density at the point opposite is just a point where the squared distance is no longer differentiable, if you think of this periodically, and there's a problem there because of that. So if you reach the uniform density there, then you might get a central limit theorem with a slower rate of convergence than 1 over square root of n. All right, so in theory now, one could use this to construct asymptotic confidence sets. Well, just by applying the central limit theorem, you would have to make a uniqueness assumption, so you would need to make some, say, shape assumptions about your distribution, symmetry, for example, unimodality, things like that. Then you need to estimate the density at the point opposite, because that enters the asymptotic variance over here. So you'd use some non-parametric density estimator, ensuring that what you're estimating is in fact smaller than 1 over 2 pi, which might create difficulties as well. So, and in order to do that, you again need some more smoothness assumptions. And furthermore, if you think of this from a more applied perspective, then you'd possibly want to check these assumptions, and they are rather difficult to check from your data set. So what I would, let me illustrate this with a simple example. where I have just an equilateral triangle. I have 3 point masses at the corners of an equilateral triangle. All point masses have are 1/3. And then the set of population Frechet means in this situation will just be those 3 points again. But if you sample from this distribution for large n, you will obtain an empirical distribution which is asymmetric with large probability. And if this distribution is asymmetric, then what will happen is that you will get a unique empirical mean, empirical Frechet mean. And opposite this empirical Frechet mean, the density will be 0, right? So everything will look fine. You will think that you're allowed to use asymptotics because you have a well-defined empirical mean, and opposite this, you have no data at all. So you think, oh, great, okay, I can just apply my asymptotic method, but of course, you may not. And what's happening here is that in this case, you have a distribution which has a whole set of population means, but if you perturb this a little bit, then suddenly the asymptotics become applicable. All right. So in this situation, what do we do? Well, what I would really like to have is a non-asymptotic universal confidence set. By this, I mean I would like to have a confidence set which guarantees coverage for any sample size n, and it guarantees coverage of the whole set of population means, and I don't want to make any distributional assumptions whatsoever, okay, except that the data are IID. And is it possible to construct this? Well, I wouldn't be here today if it were not. Yes, it is. What you can do is you use mass concentration inequalities to control the deviation of the empirical Frechet functional, which is an average, right, over the data. So an average of IID data, if you like, here. And you control its deviation from its expected value, which is just a population Frechet functional. And you can do that at every point, at every fixed mu possible Frechet mean. And then you can do the same with the derivative, more or less, except that squared distance is not differentiable at the point opposite, but you can work around that. And then you get your confidence set. So in the first step, what you can show is if you're what you can construct a confidence set where you take all those values mu, where the empirical functional is not larger than the minimum of the empirical functional plus some critical value delta. Right, this is very natural, and using these mass concentration inequalities, you can calculate what this delta could be, and this depends on another parameter over which one could, J here, over which one could optimize in advance without problems, numerically. And the proof basically is, as I told you already, you use a mass concentration inequality to control this deviation between empirical and population functional at a fixed point. And this is possible because the squared distance on the circle, of course, circle being compact, is bounded, so you're allowed to apply Höfting's inequality, say. And then you control this on a set of grid points, and since the squared distance is also Lipschitz, then it's enough to control at such grid points, and you can make an estimate in between those grid points. And with this construction, you get a confidence set which guarantees coverage of the entire set of population means with probability at least 1 minus alpha half. The problem with this approach is, if you only do this, then think of a point mass, all the mass being at a single point, 0, say, then the population Frechet function will be just a parabola, and the deviations, the fluctuations you're estimating now to be roughly 1 over square root of n. Of course, there are no fluctuations in this case, but you don't know this in advance, right? And so now this translates, if you take the square root, into a convergence speed of n to the power of minus a quarter. So this is too slow. And what's going on here? Well, of course, you should look at the derivative of this functional so that the fluctuations in the vertical axis in this empirical process, if you like, translate and the same rate into the horizontal change. And this can also be done similarly if you take care of the non-differentiability at the cut locus at the point opposite your possible mean. Again, with the same technique, you calculate a critical value, a second critical value for the derivative, and then you get a confidence set which guarantees coverage of the entire set of population means for any kind of distribution with probability at least 1 minus alpha. Let me quickly show you two simulations which are supposed to show you that this even works in situations where the asymptotics is not applicable. The first I told you about already. And in this case, if you take 10,000 IID data points from this distribution of 3 point masses at the corners of the equilateral triangle, what you get is these green segments over here, these thick segments, as a confidence set. And indeed, this confidence set contains all 3 points, right, as you would wish for. And if you repeat this whole experiment 1,000 times each for different sample sizes, you can see how the size of this confidence set decays. And it decays roughly like 1 over square root of n, a little slower. So if you consider here 10,000 to 1,000,000 data points, you have a decrease of a factor of 9 instead of 10, what you'd expect as a square root of n kind of convergence. And so this looks quite right, I would think. And in the second simulation, this example is even worse. Here, this has been cooked up by Stefan Huckermann and me in order to have a set of population means, which is an entire arc, the orange arc over here, the inner one, if you like. And so this is a kind of mean distribution. Of course, here asymptotics does not make any sense. The density on this side opposite is exactly 1 over 2 pi, constant on a whole arc. And therefore, this would not work, but with this technique that I just showed you, you can still compute a confidence set, which is the thick green area again. Here, again, it includes the whole set of population Fréchet means. Now, it doesn't make sense, of course, to ask how quickly this becomes small, because it shouldn't become too small, but you can look at the excess length of this confidence set and how this decreases. And in fact, again, you have a decrease of a factor of 9 if your sample size goes up by a factor of 100. So again, you have a order of convergence speed, if you like, which is sensible here. All right, to sum up, in some sense, these confidence sets are easier to construct, in fact, than asymptotic ones. Because for the asymptotic, you would have to estimate the density opposite and so on and so forth. And here you guarantee coverage of the entire set of Fréchet means, but this comes at a price. Then the price you have to pay for this is that they are quite conservative, right? However, the excess length is of the order of square root of log n over n, roughly, which is what you would expect from a method which is based essentially on empirical processes, like the one here. So in the future, there are some improvements that one could do easily. One is to take the variance into account. So as people who know about mass concentration inequalities know, definite inequality only uses that you have a bound on the random variables. If you know something about the variance, you could use that information too. And of course, one could consider other metric spaces, Fréchet p-means, Fréchet medians, for example, where you minimize instead of squared distance, the absolute value of the distance and things like this. All right, that's all I wanted to say, and thank you for your attention.
Okay, thank you. Are there questions or comments? Okay, maybe you have a question.
Thank you for your presentation. As I understand, your bounds are independent of distribution, yes?
Yes, that's correct.
If we fix any particular distribution, so can we obtain some better bounds?
You mean if you fix a family of distributions?
Yes. We make some make some assumptions about the probability distribution.
Well, if you consider a family of distributions,
Yes.
it depends on, of course, what kind of assumptions you make. Do you make parametric or non-parametric assumptions? If you make parametric assumptions, you might as well estimate the parameter, which is done classically in this area, and then plug in to get an estimator for the mean. But of course, you could use this here as well in this framework to sharpen the concentration inequalities, and and you might know then more about the Lipschitz constant, which enters here, which of course here you can only roughly estimate. You get that you would win, I suppose, if you applied the same program to a more restricted set of distributions. You might win in the constants, but I don't think in the order of convergence. I mean, the log factor, which is here the real problem, I don't think you would get rid of, and I suspect that it's not possible to get rid of this log factor at all if you have to look globally for means, right? So in the classical asymptotics, of course, you have here just the factor of 1 over square root of n, but this is due to the fact that you already know that there can be only one minimum of your functional. You make this assumption, but I don't have a proof yet to show that if you cannot make this assumption, if there could be several means, that the log factor here is unavoidable.
Okay. Exactly.
Thank you for the very nice talk. Well, you're computing things on the circle. So basically what you're putting into evidence here are mainly topological issues about the manifold itself.
That's right.
Do you have an idea of how you can scale, or things could be scaled up to other manifold, well, larger dimensional, where we could see curvature? And in particular, do you think there is, I mean, is it only a topological problem, the fact that you cannot always converge? Is there some issues with curvature? What is your feeling about that?
Well, I'm not quite sure what you mean with convergence here.
Well, the fact that the problems that you have with your density at the cut locus, which means that you cannot converge towards the laws of large number, is not working as usual.
That depends on the space that you're working on very much. So of course, if you, for example, consider the torus, you have the same problem. But if the cut locus has codimension 2 at least, then this, if you have a bounded density, you will not have any problems, whatever the bound on the density is at the cut locus.
Okay,
so it's a mixture of geometry and topology, if you like.
Okay. And so you expect to be able to scale up this type of techniques to other manifolds with curvature?
Yes, I mean the same techniques of the construction would work. What you really need is on a more general manifold, you need to be able to have something like a grid, say. So what would enter essentially is coverage numbers, and you would need to be able, if you want to apply this in practice, you would need to be able to construct a covering set of balls of a certain size. And then for that covering set, you could do the same program as done here, basically. Here on the circle, it's just much easier to implement, of course, because you have full control. I mean, the covering set is very easy to construct. You just use a regular grid, right? If you're using a sphere, you know that this is already somewhat harder to construct. It's possible, of course, to do. And then the same techniques would apply. So in general, this is a blueprint on how to do it on any kind of metric space, given you know how to construct such sets.
Okay, thank you.
Thank you.
Let's thank the speaker again.